Okay, here we are with the second part of chapter 13. We will be discussing proton NMR. As we talked about in the previous video, that NMR, the most common NMRs that we use to confirm the structure of an organic compound are the proton and the carbon-13 NMR. Okay, so we call this as a proton NMR, is an H1 NMR, and where we only detect the protons of the compound. Okay, so no other atom is being detected in this spectrum. So if you look at a spectrum of a sample compound here, you see there are peaks on a scale which is marked in parts per million. We'll talk about that in a little bit. But this is an example of a proton NMR. Okay, so it's only giving you an idea of what kind of protons are present in this compound. We will be talking about another type of spectrum, which is the carbon-13 NMR, where it will give you an idea about the type of carbons you have in that compound. Okay, so let's start with characteristics of proton NMR. Like, what are the most important features you should look in a proton NMR? There are four important features. One is the number of the signals. Second is the location of the signal. That means where on the scale are they located. Number means how many number of signals are there. Third is the area under each signal. So how much area is there under these signals here. And the last one is how the peaks are split, or we can call them as splitting of the signal. So like, for example, this peak is actually a single peak, but it has been split into three parts. Okay, so and this one is a single peak, and then here we see four splits in it. Okay, so that is what we will learn about in splitting. Now let's talk about first the number of signals. The number of signals in a proton NMR indicates the different kinds of proton. Okay, it doesn't tell you how many protons are there, but it will tell you the kind of proton, or how many kinds of protons are there. So for the kind of proton. So protons that occupy identical electronic environment will be chemically equivalent, and they will produce only one signal. Okay, so for example, in this structure here, there are protons at this end, right? There is a CH3. There are 3 protons here. There are 2 protons here, and there are 3 protons here. Okay, so we can use different colors to look at them. So we have this. These are 3 protons here. We have 2 of them here, and then we have 3 protons here. Okay, well, I will go ahead and use green for here for these protons. Then I will have blue for these, and then we can leave this as red color. Okay, so these are the ones in similar color, like these 3 of them. They are chemically equivalent. Okay, that means they have a very similar electronic environment. Like these 3 protons, they are next to a carbon atom or a carbonyl group, so their electronic environment is the same. Now these 2 protons are different from these 2 and also different from these. However, they are similar to each other. They're chemically equivalent to each other. Okay, and here we have 3 more protons which are chemically equivalent to each other, but they are different from these ones that are represented here. Okay, so we can say that in this molecule there are 3 sets of proton. We can call them as set A. This is set B, and this one is set C. Okay, so that's how we will identify the number of signals in the NMR spectrum corresponding to the kind of protons we have. Let's take another example. Let me illustrate this with one more example of chemically equivalent protons. So here we have a compound. It's a acetone molecule. I think you guys are familiar with it, right? This is an acetone molecule. How many signals will you how many number of signals do you expect from this compound? You will see only one signal in this molecule. Why? Because this hydrogens here, these protons, are exactly equivalent or chemically equivalent to these protons here, right? So if you plot the NMR spectrum, proton NMR spectrum of this molecule acetone, you will see only one signal because we have all these protons equivalent. If I have a compound like benzene, okay, cyclic compound, if you have a benzene compound like this, again, how many protons do you see here? 6, right? One here, there is one here, 2, 3, 4, 5 and 6, right? 6 protons. They're all equivalent, and there will be only one signal. Okay, so that's how you have to look for or you get the information about the number of signals that it tells you the kind of chemically equivalent protons. Okay, now we will talk about the rest of the 3 characteristics of the proton NMR, starting with the location of the signals. Before we talk about the location of the signals, let's understand what we mean by chemical shift. So one of the major advantages of NMR is that of knowing the position of the signals, like where the signals will appear. Just like when you studied IR spectroscopy, if you recall, we knew that if there is a carbonyl peak, then it would appear around 1700 centimeter inverse, or if it is a OH peak, it would appear close to 3000 centimeter inverse region, right? So same thing with NMR, the position of the signal gives us information regarding the environment, chemical environment of the proton in question. Okay. Now, for understanding the position of the signals, we need to refer it to something which will help us to know relative to this reference peak how much shift has happened. Okay, so this reference peak is that we use is that of TMS. Okay, and TMS stands for trimethylsilane. Okay, it is a compound of silicon, so silane, Si. Then we have CH3, it's tetramethylsilane. So there are 4 CH3 groups. So we have 4 CH3 groups here. This is the compound whose signal is taken as the reference signal, and we take that as appearing at 0 parts per million. Okay. Now, the good thing with this using a chemical shift is that it is this chemical shift of the protons is going to be the same regardless of the operating frequency of the spectrometer. So you can run the NMR spectrum in a 60 megahertz spectrometer or a 300 megahertz spectrometer or a 900 megahertz spectrometer. However, the position of the signal for that type of proton will always remain the same. Now, for example, this peak I have drawn here is for a benzene molecule, which has only one set of protons, which are all chemically equivalent. So you will get only one signal. And here is where the signal appears, around close to 7.27. Okay, this is a table which kind of tells you where you can find protons on the NMR spectrum. This is for a proton NMR spectrum. The range of the scale goes from 0 ppm to like 12 or to 15 ppm. Most of the protons, or almost all the protons of the organic compounds, can be found in this region that's shown. So if you have a CH3 group in your molecule, then the chemical shift usually is in this region of 0.73 to 1.3. If you have a CH2, 1.2 to 1.6. All right. Now, here you can see that X stands for halogen. As you start putting electronegative elements close to the proton in question, then the chemical shift starts to increase, right? Or you can say that we move more what is called as a downfield. So let me tell you what we mean by this downfield and upfield. In an NMR spectrum, the left side of the spectrum is called downfield and the right side of the spectrum is called upfield. So when protons are close to an electronegative element like halogen or oxygen or nitrogen, then the inductive effect of this electronegative element causes the proton of this methyl group or a CH2 group to be de-shielded. That means they are surrounded by less electron density, and as a result of which the signal, which usually would have appeared in this region, now will appear more downfield because they are de-shielded or from the external magnetic field. Okay, so if the shift happens downfield, that means they are de-shielded from the external magnetic field. If they are appearing more upfield, that means they are more shielded. Okay, so we are talking in terms of their effect from an external magnetic field. So more the electronegative elements present in the molecule and the protons close to the those electronegative elements, they will appear more and more on this downfield part of the spectrum. Okay, and you can clearly see it here that when we are looking at an aldehyde here, see, look at this one, the aldehyde proton, it appears almost at 9.7 to 10 ppm, much down here. Okay, here, let me see, yeah, over in this region. Same thing with a carboxylic acid, and the carboxylic acid proton appears around 11 to 12. That is, it is surround close to two electronegative elements, which are two oxygen atoms. Therefore, they appear much downfield. How about the vinylic protons? So if you have protons on a double bond or the protons on a benzene ring, they also, if you look at carefully, you will see that they are also appearing at a little downfield region, right? So why we explain this using the term anisotropic effects. Now the chemical shift of a proton is sensitive to the diamagnetic effects resulting from the motion of pi electrons too. So now this is rich in pi electrons, same thing with here, and this effect causes the and this anisotropic effect causes the protons to shift more downfield. And there are other regions which you may need to look from your textbook. However, you will be given a table like this when you are solving your NMR problems, so that you don't have to memorize these values since you are still beginning of NMR and you're practicing problems. So I would let you use a chart which has the chemical shift values. In that way, it becomes a little more easier for you to analyze the NMR spectrum. Okay, now we talked about double bond protons, we talked about close to electronegative elements. Now let's do an example before we wind up this location signals topic. If you have a compound like this, the question is, could you tell me which protons would appear the most downfield? Okay, so for that, first of all, you need to figure out how many kinds of protons are there. So we have protons here, right? This is all equivalent. So you will have a signal for this group. There are two protons here, so you will have a signal for this. And then there are these three protons, so which are all chemically equivalent. So you will have a signal for this one too. Okay, now here we have a CH3 group and a CH2 group which are close to an oxygen atom, which is electronegative in nature. There are no hydrogens here, remember it's a carbon with 4 bonds. So these set of protons will appear downfield, whereas this will appear more closer towards the upfield. Okay, so that's about the location of the signals. The next topic which we would like to cover is about the integration. Now integration tells you about, integration means the area under the peak. Okay, it tells us how many protons are under these peaks. So for example, in this is a proton NMR spectrum of a molecule that's shown here. You can see that there are two sets of protons. One set here, there are hydrogens here, right? There are 3 hydrogens. Same thing, hydrogens here, and we have hydrogens here. But these, all of them, they are the same. They are all chemically equivalent. And then we have a set of hydrogens here, which are actually different from these, but they are equivalent to each other. So we can call them as set A, and then these can all be bunched up together and called as set B, right? All these protons. So now which one do you think will be A here, and which one do you think is B? From our previous slide, we talked about that if the protons are close to an electronegative element, they will appear much downfield, right? So this is the downfield part of the spectrum, this is the downfield, and this is the upfield part of the spectrum, right? So these are the protons which will appear downfield. So this is my proton A, set of proton A, and these are the proton B. Okay. Now if the NMR spectrum were to be integrated, then it will tell us that this peak corresponds to 9 protons, because we have 1, 2, 3, 4, 5, 6, 7, 8, 9, right? And this corresponds to 3 proton. Okay. So the area under the peak is what is called as integration, and this value indicates the number of protons that gives rise to each of this signal. The third and the final characteristic of the proton NMR spectrum is the multiplicity, or we can talk about it under this heading of splitting. Okay. Now multiplicity is defined as the number of peaks in the signal, right? So for example, let's take a look at this molecule. So if I ask you how many equivalent protons or non-equivalent protons are there, you can say that there are 2 non-equivalent sets of protons, right? So we have a set here which is exactly the same as here, and then we have a set here which are both similar, right, or chemically equivalent. So that is, we can again label them as A and B. Okay, we can use colors to designate that. So say for example, I have these protons shown as red. Now these are chemically equivalent to these protons, so they both will appear as one signal. I mean this set and this set, let's call them as A. So they both are A. And then we have another set here which we can put them as blue in blue, and we have protons here, there are protons here, we can call them as set B, and they both are chemically equivalent, right? So both the B's appear as one signal, and both sets of A's appear as one signal. Okay. Now can you predict which one would be A and which one would be B in this case? Remember that the one that is closer to the electronegative element is shifted downfield, so this should be my B signal and this should be my A signal. Okay, so I expect one peak, but actually what happens, what do I see in my actual NMR spectrum is there is a split in that signal, right? So this is what is meant by multiplicity. There are different kinds of multiplicity that has been observed. If the peak appears as just one single peak, we call it as a singlet. If it appears as 2 peaks like this, then it is called as a doublet. If you have 3 peaks like this, it's called triplet. And if you have 4 peaks like this, then this is called as a quartet, and so on. There is a you can have a quintet with 5 peaks, sextet with 6 peaks, and septet with 7 peaks. Okay. Now you should also note that these peaks there's a ratio to these peaks, right? If it is a singlet, that's like it is a we don't have to talk about a singlet, right? It's just a single peak. But for a doublet, if you look, the ratio of the 2 peaks is about 1:1. When you have a triplet, the ratio is always 1:2:1. When it is a quartet, okay, we will always have the ratio of 1:3:3:1. Okay, and that then if you write down the quintet and the sextet and the septet, this ratio, this kind of we call it as a Pascal's triangle, and that is what is followed. So let's see how this splitting happens. Okay, a signal's multiplicity is the result of magnetic effects of neighboring protons. So it has all to do with neighboring protons. So how a signal of A will be split will depend upon what kind of protons you have as its neighbor. Same thing with B, its splitting will depend upon the magnetic effects of this neighbor that is called as A. Okay, so let's take this example and try to illustrate it. This is a ether again, it's diethyl ether. Now the methyl protons, which are these, which will be labeled as A, when it are subjected to the instrument's magnetic field, right? We know that we have placed them in an external magnetic field, but they can also feel the tiny magnetic fields generated by the nuclei of this CH2 group also, right? Because remember, we talked in the beginning of the lectures in the chapter 13 that these protons actually behave as tiny magnets, right? So they are not only affected by the external magnetic field, but also affected by these neighboring protons, which are also behaving as small magnets. Okay, so these are the ones that will cause them to split. So A will be split by B, and similarly B will be split by A. Now what is the rule we will be using for analyzing how many splits will happen is n plus 1, where n is the number of neighbors that the chemically equivalent protons have. Okay, so we will use the n plus 1 rule. Okay, let me go back and use my black pen. So it is n plus 1 rule, where n is the number of neighboring protons. Okay, so if we have n number of neighbors, so we can call them as n is a neighboring proton. If A has 2 neighbors, so how many splits will you get for A? 2 plus 1, that equals to 3. So that is why you can see that the signal at A for A appears as a triplet. Now how many neighbors does B have? It has got 3 neighbors, so it will be split into 3 plus 1, 3 plus 1, and that is why it comes as a quartet. If it is 4, so 3 plus 1 is 4, so it has got a quartet type of splitting pattern. Okay, now what do we call as neighbors? So for our analyzing purposes, we will use any proton that is 3 bonds or less apart. Okay, so anything more than 3 bonds is considered to be too far and not considered to be a neighbor. Okay, so my point is that, say for example, if you're analyzing this proton, so which one would be its neighbors? You can say that something that is 3 bonds apart. So we have this 1 bond, 2 bond, and this is the 3rd bond, right? So any protons that are present 3 bonds or less apart, then they will cause splitting. Anything that is further, so this set A will not be split by these protons because they are very much farther, or they're not considered as neighbors.